Hi, my name is Ramneet Kaur and I will be doing the voiceover for the AP Calculus BC Chapter 9A notes. Okay, so we are going to start with 9.1, which is sequence. A sequence, otherwise known as A of n, is known as a set of terms commonly set up as A1, A2, A3, where you're plugging in the 1, 2, or 3 as the n, and the n is a positive integer. A of n is known as the nth term. A of n plus 1 is the next term. A of n minus 1 is the term before the nth term. Also, A of n as n equals k and approaches infinity is usually the start at the kth term. This is an example of listing of a sequence. So if A of n equals n over 1 minus 2n, when you plug in n equals 1, you get negative 1 on top over 1, because when you plug in 1, it'd be 1 as n over 1 minus 2 parentheses 1. The bottom denominator would be 1 minus 2, which creates a negative 1. You could bring the negative up to the negative 1, so altogether it'd be a negative 1. And it continues on as you plug in n equals 2, n equals 3, n equals 4, and n equals 5, creating the numbers listed below. This is another example of listing of a sequence. So if A of n equals n squared over 2n minus 1, when you plug in each n into the equation, when n equals 1, it would get you 1 over 1, because the top would be 1 squared over the denominator as 2 to the first power minus 1. The top would be 1 over 2 minus 1, which is 1 over 1. The second one, when plugging in n equals 2, would be the numerator as 2 squared over the denominator as 2 to the second power minus 1. Top would equal 4, as seen below, and the bottom would be 4 minus 1, which is 3, given to be 4/3. And the numbers continue on as you plug in an increased number of n. This is a different example of finding a sequence. The sequence given to you is 2, 3 over root 2, 4 over root 3, and 5 halves. So to figure this out, you would separate each term knowing that 2 is A of 1, and 3 over root 2 is A of 2, 4 over root 3 is A of 3, 5 halves is A of 4. So when listing them out separately like this, you could differentiate it more. The first step to do this, you would create them and put them into the same form. For example, 2 is over root 1, commonly how the first, the second, and third forms are. The second, third form are already in the number over root of the number below. But the fourth, you would change it to 5 over root 4, because root 4 would simplify to 2, which is the original number given to you. Next, you would relate the terms to n. So as seen in the third step, what was done is 1 plus 1 equals 2, commonly like the original given to you, over the root 1. For the second term, 2 plus 1, which would equal 3, is over root 2. And for the third one, 3 plus 1 over root 3, 4 plus 1 over root 4 for the fourth one. A common theme seen in this would be n plus 1 over root n, as seen below. For example, how it is for A of 1, which is 1 plus 1 over root 1. For 2, it's the second term, it's 2 plus 1 over root 2. So you could see the n plus 1 over root n in the rest of the terms, which is your given equation for a of n. The nth term is usually known as the last term. Two parts of it would be convergence, which is the sequence value is heading to a specific value. A pattern that could be given by this is 1, 2, 3, 4, 5, and so on, because you know what the next number would be knowing the pattern. Divergence is something different. The divergence is the last term and it is not headed to a specific value. For example, a list could be 2, 4, 2, 4, and so on and so forth. Also, divergence could be known and connected to the number infinity. This is an example of trying to find out whether the a of n is divergent or convergent. So in this, the a of n is n over 1 minus 2n. To figure this out, you would set it to be the limit as n approaches infinity. So when you set it up as limit n approaches infinity of n over 1 minus 2n, when you plug in infinity into the n's, you would get infinity over 1 minus 2 times infinity, which is infinity over infinity. Since you can't do that, you would have to do the L'Hopital's rule and do the derivative of the original problem, which would give you a 1 on top and a negative 2 on bottom. So you would continue on by doing the limit as n approaches infinity of 1 over negative 2. Since there is no n in the problem now, you could have your answer be negative 1/2, which would be convergent because you know that it is going to a specific number. Something to note down is if a limit of a sequence, a limit as n approaches infinity of a of n, if the limit exists, then the sequence converges. But if the limit does not exist, then the sequence diverges. An important theorem to know is the absolute value theorem. This is if a limit as n approaches infinity of absolute value of a of n equals 0, then limit of as n approaches infinity of a of n would equal 0. An example of this would be limit of n approaching infinity of parentheses negative 1 to the nth power over 3 to the nth power is given to you as your original function. You could consider limit as n approaches infinity of absolute value of parentheses negative 1 to the nth power over 3 to the n close absolute value sign. You could do the absolute value and plug it in, and you would know that negative 1 to the nth power would cancel out because it's a negative, and that cancels out with the absolute value sign. Therefore, a limit as n approaches infinity of 1 over 3n would equal 0, because when plugging in infinity to the n, it would give you 1 over 3 to the infinity, which is 1 over infinity, and 1 over infinity is 0. A monotonic sequence is also important to know. So for a monotonic sequence, if it always increases, it would be an example like a of 1 is less than a of 2 less than a of 3 and continued on, or it's decreasing. A of 1 is greater than, a of 2 is greater than a of 3 and continued on. For a monotonic sequence, it has to always increase or always decrease for it to fit. For a bounded sequence of a of n, if a of n is less than or equal to m, then it is bounded from above. If a of n is greater than or equal to m, then it is bounded from below. If m is less than or equal to a of n, which is less than or equal to another m, then it is bounded and between the m's. If the sequence is monotonic and bounded, it would mean that it converges altogether. So it must be monotonic, which means always increasing or always decreasing, and it must be bounded for it to converge. This is the end of 9.1 sequence. Continue to next lesson of 9.2 series in the next video.